All right, subscribers, welcome back to another episode of Science with Surbeck. Today what we're going to be talking about is section 6.2, which talks about classification of the elements. Our objectives for this lesson is to, 1, explain why elements in the same group have similar properties, and 2, identify the 4 blocks of the periodic table based on electron configuration. All right, so we start out here and we start this section off by discussing valence electrons. Now, valence electrons are electrons in the highest principal energy level of an atom. Now, elements in the same group have the same number of valence electrons and they have the same chemical properties. So what we can say about this is that atoms in the same group are going to have similar chemical properties because they have the same number of valence electrons. Now, point 2 and point 3 here are very key points to this whole entire section of notes. And before we go anywhere, I want to identify once more the number of valence electrons found on each and every group in the periodic table. So with a periodic table, remember, we can divide it into those groups and we can identify the valence electrons, which, as a reminder, the valence electrons are going to be abbreviated as VE. So any element in group 1, hydrogen all the way down to francium, will have 1 valence electron. Any element in group 2 will have 2 valence electrons. We skip over the transition and intertransition metals and we get to the group with boron that has 3 valence electrons. Carbon has 4 valence electrons. Nitrogen has 5 valence electrons. Oxygen has 6 valence electrons. Group with fluorine has 7 valence electrons, and our noble gases have 8 valence electrons. So again, this is a reminder about how valence electrons are related to the periodic table. Now, as we continue going on in this discussion, even though the elements in the same group have the same number of valence electrons, they don't actually have the same number of total electrons. And this shouldn't be some common sense here. But as we go down the group, the energy level is going to increase, which means, again, the period number or the row that we are in also increases. So if we look at lithium and gallium, lithium has the valence electrons in the second energy level because lithium's in that second row, whereas gallium, it's in the 4th row and it has its valence electrons in the 4th period. So as you go down the group, your valence electrons are going to get in a higher and higher energy level. And just putting words to what I said here, as we go down a group, your valence electrons, VE to the minus, get in a higher energy level or are in a higher energy level. Okay, so what we get into here is that business about the transition metals, or why we skip over that. Okay, so representative elements have a distinguished number of valence electrons. We went over that while we are writing on the periodic table and as we have this set up here. Now, what we need to talk about here is one exception, and this exception is in our transition metals. So for us in general, again, this is going to be an in general statement that all are going to have 2 valence electrons. And so I'm going to write this down. I'm going to write in general, and I'm going to also write exceptions occur. Okay, so we can add to our periodic table. So in general, our transition and intertransition metals are going to have 2 valence electrons. There are some exceptions to this particular policy, but in general, our transition and intertransition metals have 2 valence electrons. And this can be explained through electron configuration. So let's say we have the element scandium, okay? So we have scandium, and I'm going to go ahead and write down the electron configuration for scandium. So the electron configuration for scandium would look like this. Now, the highest principal energy level is the 4th energy level. So I'm going to mark this as the highest energy level. And because there are only 2 electrons in that highest energy level, there is only 2 valence electrons. So again, the valence electrons are determined off of the highest energy level. Because scandium only has 2 electrons in that 4s level, that is why it only has 2 valence electrons. All right, so now what we're going to do here is we're going to correlate those different blocks, the S, P, D, and F blocks, to our periodic table. And we've already done this, so it will be a fairly quick review. But remember that these subshells are representative of the locations for each electrons. So you can kind of think of it as, again, specifying an address for our particular locations where an electron can be. Now, what we have to think about here is what valence electrons are occupying these particular blocks, okay? So as we go through this process, we want to identify what electrons are occupying these particular blocks. So we start off here with our S block. And our S block elements are going to consist of group 1 and 2. And as you can see here on the periodic table, the S block is shown in groups 1 and 2. Now, the valence electron of S block elements only occupy those S orbitals. So these things here, the valence electrons, are only going to be in that S block of a particular energy level. All right. Now, we will repeat this, and you'll write this down quite a bit. S orbital has, or S sublevel has 1 orbital. Now, each orbital can only hold 2 electrons. And this is why when we wrote our electron configuration and we represented that through our orbital box diagram, we said that S had 1 box to represent 1 orbital. And we'll note this on all of these as we go through our examples. All right, so the next thing that we went over when we talked about our orbital box diagram or our electron configuration was that P block. And P block consists of elements in groups 13 through 18, and the valence electrons occupy in S and P orbitals. Now, specifically here we see this again. A P sublevel contains 3 orbitals, but those orbitals can only hold a maximum of 2 electrons. So again, we write that we have our P orbital, and the P orbital, if we remember from the orbital box diagram, was only going to have 3 boxes. So our three boxes represents our 3 orbitals that we have in a P level or a P sublevel. All right, so what we need to consider this is our noble gases. Now, noble gases are on the right-hand side of the periodic table, but what makes the noble gases so inert or so unreactive is that they fill their outer s and p orbitals. What that allows that atom to be is be very structured. Now, the more stable or structured an atom is, the happier it is, meaning the less reactive it is. So this is a very key takeaway, especially as we transition to our ionic and covalent bonding. Again, 8 electrons here is going to be seen over and over and over again as we go through this particular process. All right, so moving on here to our D block elements. Our D block elements are going to consist of elements 3 through 12, or that are in groups 3 through 12. Now, their valence electrons only fill that s orbital. We did a great example here with our scandium atom. And maybe I'll put that in notes here, is our example was scandium, okay? And we did that earlier in notes. Now, the D sublevel contains 5 orbitals, but again, each orbital can only hold a maximum of 2 electrons. So our D orbital, if we drew our orbital box diagram, would consist of 5 different boxes. So the D orbital contains, or the D subshell contains 5 boxes, which we use to represent 5 orbitals. Now, again, we see that scandium example there. We've went over that in notes before. There's no need to rewrite the wheel. All right, so our last set of elements is our F block elements. And our F block elements are consisting of those inner transition metals, and they only fill those s orbitals. Or better stated, their valence electrons only fill their s orbitals. Now, the F sublevel consists of 7 orbitals, which if we go back to our orbital box diagrams, we represent that with our 7 boxes. And these would represent our 7 orbitals. All right, so now we have to talk about our example here. And I am just going to go ahead and I'm going to write out the electron configuration of cerium. So cerium, if we take a look at cerium and we write the electron configuration, we would get this. Okay, so the highest energy level is our 6th energy level, okay? So I'll put this here as our highest energy level. And there's only 2 electrons in this level, and so therefore, once again, we only have 2 valence electrons. All right, so we have correlated a lot about electron configuration and how this relates to the periodic table. And the important takeaway here is matching up, okay, well, what or where are those valence electrons being filled for your particular atom? Hope you've enjoyed this episode as always. And if you haven't done so already, make sure you subscribe.